Okay, so this is Unit 9, Day 1, and now we're on page 4 of our notes, and we have some special cases of limits. In example 5, we see the limit as x approaches 0 of x minus cosine x over 1,000. If you look at the graph, it looks very clearly like our limit would be 0 right here. But if you examine the table of values, you can see that that graph tricked us, and the limit is actually exactly negative 0.001. Now we could have found that limit by plugging 0 into our function. We would have 0 minus cosine 0 over 1,000. And remember that cosine of 0 is 1, so that would be 0 minus 1/1000th, which gives us the negative 0.001. So you have to be careful looking at a graph. Sometimes if you're thinking that the value may be 1, you can look at the table of values to be more exact. And the limit here is negative 0.001. In example 6, we see an example of oscillation. Oscillation is one way that a limit may not exist, and it's oscillating wildly. So oscillating, you know, is moving back and forth, but this function is oscillating wildly, and when that happens, our limit will not exist. This is different from the normal oscillation of a sine function. So if you think of a sine function, the sine function goes up and it goes back down again, and it goes up and it goes back down again in a very predictable pattern. So that if you were to zoom in on just a very small piece of this function, it would look almost as normal as a straight line. If you look at this piece right here, that almost looks like a line. Very predictable. Yes, your limit can exist here. But this function, sine 1 over x, if you were to graph that on your calculator and zoom in, you will actually find that this gets crazier and crazier the closer you look at the function. So as you zoom in closer and closer, it gets more and more wild. And for this reason, we cannot actually approach 0 and find a limit. So this limit does not exist. And this means that oscillation is one of our reasons why a limit might not exist. Oscillation. All right, I saved number 1 for our most common reason why this limit would not exist, which is that you're approaching different values from the left and from the right. So the limit does not exist when the left-hand limit does not equal the right-hand limit. And then the third reason when the limit might not exist is if you're going to infinity or negative infinity. Remember that we write infinity or negative infinity as our answer, but that's actually a special case of does not exist. So I'll just write infinity there. All right, so we have 3 more examples here. I'm just going to number them 1, 2, 3 to keep track of them. In example 1, we're looking at a function and we're trying to approach 3 from the left. So I'm just going to do that with a table of values, x and y. And I'm going to choose numbers to the left of 3. So I'm going to choose 0, 1, 2, 3. When I plug 0 in, I get 3 over the absolute value of negative 3, which is 3 over 3, which is 1. And you find that if you plug in 1, you get 1. And if you plug in 2, you get 1. But if you plug in 3, you get 0 over 0. So 3 minus 3 over absolute value, 3 minus 3, is 0. And that's because there is a hole in this graph. So this is a value that's undefined. So the limit as you approach 3 from the left, you are going to be at 1 all the way along until you get to your hole. So this limit is 1. That's your answer. Problem 2 is talking about a piecewise function where when you are less than 2, you have this linear function, and when you are greater than 2, you have this quadratic function, and right at 2, you have this value of 8. So what we're going to do is find your left-hand limit and your right-hand limit and see if they're the same. I'm going to do the limit as x approaches 2 from the left of f of x. And I'm going to find that by plugging 2 into this function on the left. So that would be 3 times 2 plus 1, and I get 7. And then I'm going to do my right-hand limit. I'm going to do the limit as x approaches 2 from the right, and this was my left function. This one down here is my right function. So I'm going to write f of x here, and then I'm going to plug 2 into the function, 2 squared plus 3, and I get 7. So on the left side I'm approaching 7, on the right side I'm approaching 7. It doesn't matter that the actual value is 8. All that matters is I'm approaching the same number on the left as I am on the right, and that is going to be my limit. So my answer is 7. Decide if the following are sometimes, always, or never true. If the limit does not exist, then the right-hand limit does not exist. That is sometimes true. We saw an example with the absolute value of x over x, where we were approaching -1 and we were approaching +1. So on one side we were approaching -1, on one side we were approaching +1. The right-hand limit did exist, however, the overall limit did not exist. And we saw other examples where the right-hand limit did not exist. Where the overall limit did not exist, but the right-hand limit did exist. Oh, that's what we just saw. But we saw examples the other way as well. So this one is sometimes. However, if the right-hand limit does not exist, then the overall limit cannot exist, because you have to have a value on the left and on the right, and they have to match up in order for the limit to exist. So this one is always true. All right, let's turn the page. On the next page, we have a lot of rules for limits, and luckily these rules are very straightforward. They tell you that exactly what you would have wanted to do with your limits, you get to do. So that, for example, if you have the limit of a sum of two functions, you can just find their separate limits and add them together. And the same thing with your quotient rule. If you have the limit of the quotient of two functions, you can find the limits of them separately, and then you can divide them. So that's very straightforward, and even though it looks a little confusing with all of the representation here, if we go straight to the examples, we'll see how they apply. So in today's notes, we're going to mostly get straightforward answers, but if you do get the indeterminate form of 0 over 0 or infinity over infinity, that means there's something we can fix and still find the limit. So you're going to fix your function if you get one of these indeterminate forms. Today, though, most of our answers are going to be straightforward. I'm going to go to example 3 first, because I think it's an easier example to see what we're going to do. We're doing, in example 3, we're doing the limit as x approaches 1. And so I'm going to plug 1 into the function. I'm going to substitute it in. 4 times 1 squared plus 3. When you substitute it in, you should get 7. So this is a continuous function, and you can see that as you approach 1 in your x values, you'll approach 7 in your y values. The next function is a very similar function. I'm going back to 2. This is just the function y equals x. So if you take your x value, -4, and you plug it in, you can see it still is going to be -4. And then if we go back to 1, this is a constant function. It's the function y equals 3. So y always equals 3. It doesn't matter what x is. So as x approaches 1, the y is still going to be 3. All right, as we go down here, these are definitely problems where we can just substitute our x value in. So I'm going to substitute 1 in for x. I get 2 times 1 minus 1 over 1 cubed minus 2, and I get 1 over -1, which is -1. And in 5, I'm going to substitute 0 in, so I have square root of 0 plus 4, which is square root of 4, which is 2. And this one, I have 0 squared times the cosine of 0. Remember, cosine of 0 is 1, so I have 0 times 1, which is still 0. And in the last row, it's more of the same. I'm going to plug in my x values, so I have 5 times 1/2 plus 7, 2.5 plus 7, which is 9.5. I plug in the 4, I get 3 times 4 over 4 minus 3, which is 12 over 1, which is 12. And this last problem looks tricky with the e, but it's just a constant function. Y equals e means straight across y is always e. It doesn't matter what number x is approaching. Your answer will always be e. Okay, let's turn the page. Now we need to draw functions such that the limit does not exist at these values. So we have three choices, remember. You can make the left-hand limit not equal the right-hand limit. You can go to infinity, or you can do oscillation. So in problem 12, I need to mark x values of 1, 2, and 3. And maybe I will make, at 3, I'll make a function where the left side and the right side don't match up. So say I do something like this. So at 3, I'm approaching different values from the left and from the right. And I can do something similar for 2, so that I'm going to approach different values and maybe even do something like this. And then if I want to create an asymptote at 1, I can show that maybe it's because I'm going to infinity that this limit does not exist. But for 13, just to do something different, I'm going to use oscillation. So here's oscillation at 0, and at -2, and at +2, and I'm going to see if I can create something like that function that was oscillating so wildly, something like that. So this is another reason why the limit might not exist. In 14 through 19, we have two functions, f of x and g of x, and we know the limit as x approaches c for each of them. The limit as x approaches c for f of x is 2, and the limit as x approaches c for g of x is -3. So because of all the rules on the previous page, we can just take these values and plug them straight into the functions and find our answers. So you should try that before watching the video. Try it and see if our answers match up. I'm going to do square root 2 times 2 minus 4 times -3. I get the square root of 16, which is 4. I'm going to plug in 2 for f of x, so I have 2 plus 1, the sum cubed, and I get 27. And in 16, I have 2 times 2 plus 3 times -3 over -3 minus 2, and I get -5 over -5, which is 1. And in 17, I have 2 times 2 times -3, which is -12. And let's look at the next two. In 18, f of x is 2, g of x is -3. So using order of operations, I'll add these first, and I get 2 times 0, which is 0. And then this last one, f of x is 2, so 2 squared over 1 minus -3, which is 4 over 4, which is 1. And at the end, I have our formal definition of continuity. So you'll remember in the past, we said a function's continuous if you don't have to pick up your pencil. So we knew that a function was not continuous if there was an asymptote or if there was a hole. These would be ways where the function would not be continuous. But this is our formal definition over here. In order to be continuous, the function needs to have these three parts. Part 1, the function has to be defined. Part 2, the limit has to exist. And part 3, the defined value has to equal the limit. So in part 1, a function is not defined, for example, if it has a hole or if it has an asymptote. So these are not continuous functions that I'm drawing on the right. In part 2, if the limit doesn't exist, that might be because we're approaching different values from the left as from the right. And in part 3, it's possible for the function to be defined and the limit to exist, but they're just not the same values. So that might be if you have a hole in your function and it's defined somewhere else. So here's your defined value, here's your limit, they're not the same number, so the function's still not continuous. So on the next page, when we do our classwork problems, we're going to use this three-part definition of continuity to decide whether or not a function is continuous. So I'm going to stop this video here, and I'm going to do one more video for the classwork problems.